These are the examples that I worked on in class with you. Let's take a look at the first one. The size of a tumor S in cc's is a function of the number of weeks W of that treatment. What is the meaning of S of 3 equals 1.5 and S prime of 3, or in other words the derivative at 3, equals negative 0.3? When would you predict the tumor will be gone, and what was its original size? Now, I should have said this right at the beginning, but it may be helpful for you to actually have these problems actually printed out so that you can refer to them. Okay, well, let's take a look at the solution. First of all, what is the meaning of S of 3 equals 1.5? Well, I'm telling you basically that 3 is the W, or in other words, after 3 weeks, S equals 1.5. So 3 is the number of weeks, and 1.5 is the size, or 1.5 cc's. So in other words, at the 3-week mark, the size of the tumor is 1.5 cc's. How about that second piece? What is the meaning of S prime of 3, or in other words, what is the derivative at 3 equals negative 0.3? Well, first of all, you need to think about your Leibniz notation. Think of it as ds over dw, or kind of like the change in S over the change in W, just like you do with slope. The units are cc's per week. So this would be translated to mean at the 3-week mark, the tumor is shrinking at 0.3 cc's per week. That's a mistake. The 1.5 was actually negative 0.3. I'll just cross that out and put a negative 3 or 0.3 there. So again, at the 3-week mark, the tumor is shrinking at 0.3 cc's per week. And I know it's shrinking because it's negative. If it were increasing and getting bigger, then it would be positive 0.3. Okay, let's take a look at the next piece. My question was, at what point would you predict that the tumor will be gone? Well, remember, it started at 1.5 cc's. And it was going down at 0.3 cc's per week, or in other words, 0.3 times the number of weeks. So if I take 1.5 and I subtract the 0.3 per week times the number of weeks, at what point will that be equal to 0? And quite simply, if you solve the equation, you get 5. Now, to be honest, you could just sort of count your way down. After one more week, the tumor would be 1.2 in size. If I take away another 0.3, it would be 0.9 cc's in size, etc., etc. And it would take 5 more weeks, or in other words, at the 8-week mark, the tumor will be completely gone. The next question was, what was the original size? Well, let's use the same formula again. And you could think of it, again, as being 1.5 cc's going down at 0.3 cc's per week. But since I want the size 3 weeks ago, the original size, in other words, I'd have to multiply by negative 3. Now, I'll be honest, this isn't really the way I would think of it. Here's how I would think of it. It's 1.5 cc's in size right now. For every week I go back in time, it was 0.3 cc's bigger. I'm going to have to go back 3 weeks for a total of 0.9 cc's bigger than it is right now at the 3-week mark. I'll add that to my 1.5, and I'll get, and I forgot the decimal point, 2.4 cc's in size when the treatment began. Let's take a look at example 6 now. there's a chart, and the chart that I gave you shows weight as a function of height. What is the rate of the weight change at 62 inches? In other words, at this point on the chart, what is the rate of the weight change? Well, now a 62-inch individual weighs 200 pounds. The prediction for a 59-inch individual is 170 pounds. And the prediction for a 65-inch person is 240 pounds. So what we're going to have to do is figure out the slope, or the average rate of change, between the 59 and 65, because those are the best units that we have, frankly, or the closest units we have to 62. So let's go ahead and do that work. Again, slope, or the average rate of change, is the change in x, or change in y over the change in x. You went from 170 to 240 pounds. So if I subtract my 240 minus 70, the increase in weight is 70 pounds. The increase in height, the change in x, went from 59 to 65. So if I take 65 minus 59, I get 6 inches. So if I have 70 inches divided by 70 pounds divided by 6 inches, I get 13.3 repeating, or rounded, 13.333 pounds per inch. So every time I have a person that's 1 inch taller, that individual would weigh 13.3 repeating pounds more. So how would I find the weight of someone who's 60 inches tall? Well, I know the person that's 59 inches weighs 170. If I want the person that weighs 60, that's 1 inch more, which corresponds to an increase in 13.3 repeating pounds, and gives me a prediction of 183.33. Now, let's predict someone who weighs, and I'm going to change this up a little bit on you. We're actually going to find the weight of someone who weighs, the weight of someone who is 61 inches in height. Well, again, at 59 inches, I know that they are 170 pounds. If I add another 13.33, I have the 60-inch person from the last problem. So to find 61 inches, I'll need to add another 13.3 repeating, which gives me 196.6 repeating, or 196.667 in rounded form. Finally, problem 7 had to do with finding or predicting from a graph what the slope is at a given point. Now, what I've given you here is a cubic curve, but honestly it's not important to know that. What I want you to do is to predict the value at this point right here. In other words, when x equals 1. And you can hopefully see that this is my y-axis, this is my x-axis, here is my function, my y equals x cubed, frankly, and I want to predict the slope of the curve, or the instantaneous rate of change, right there at x equals 1. Now, I'll do that by coming up with a straight edge. I'm going to lay it down until I have approximately the tangent line, and I will apologize in advance. This is hardly perfect, but you get the idea, I hope, here. And what I'll do with my straight edge is draw this tangent line, which will be very fuzzy because of the thickness of the line, as far as I can. And I'll find the slope of this line by finding the slope between this farthest point up compared to the farthest point down. Now, I would estimate that this point right here, actually not estimate, because it looks like it hits the exact coordinates of that point. And the coordinates of that point would be 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9. So the coordinates of this point would be 4, 9. Let's take a look down here. And to be honest, this comes awfully close to this whole number point here. So since we're just estimating, and for purposes of my example, let's figure out the coordinates of this point right here. Well, here's my origin again. I would come down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and over 1, 2, 3. So the coordinates of this point would be -3, -10. Now, let's find the slope of that entire line. And of course, the slope at any point along that line, including this point right here, which is the one I want, where it touched the curve at x equals 1, will give me the instantaneous rate of change, or the slope of this tangent line at this point, which quite frankly gives me the value of the derivative of f of x at that point 1. So I'm finding f prime of 1. Now I apologize, the paper here could be a little better for doing my work, so let's actually use the back of this paper. My actual equation, just for the record, was f of x equals x cubed. And at this point, I'm going to want you to approximate the value of the derivative at 1. Or in other words, we're finding the slope of the tangent line at 1, or the instantaneous rate of change at 1. And because it's a graph we're doing this with, of course, this will only be a gross approximation. So first of all, I want you to notice that I dropped all the way from, actually I'd rather do it the other way. I came up from -10 all the way up to +9. My slope is, of course, the change in y over the change in x. So I went up 19, or my rise, if you prefer, is 19. I came over from -3 to +4. So I moved over 7. And of course, I know the slope is positive because the line is increasing. And if you do the arithmetic here, you'll get approximately, rounded form, about 2.7. Now, this is a little bit off, and frankly, I knew it would be a little bit off, to be honest, because I actually knew the answer to this problem before I started it. And those of you that have had calculus before perhaps knew that the value of the curve, the value of the derivative rather, was 3x squared. And the value at 1 would be 3. Now, I'd like you to see that I'm actually a little bit less than 10% off. That's actually pretty decent. If you're even a little more than that off on your test, I'm going to give you full credit. So on this problem, for certain, I'd give you credit for anything between 2.5 and 3.5, and depending on the problem, perhaps even a little bit more. So again, when you estimate what the slope of the curve or this tangent line to a curve at a given point is using a graph, you're just going to be close. And to be honest, that's all I'm ever after.